All right, so another day, another quick stream. Um, so today I'm going to be talking, or rather, my idea was to look at something that, again, I've been working on is it's uh, asynchronous programming in an embedded context. So how does that work? Because when we talk about things like async await in a standard environment, we know that we have things like, at least in Rust, we've got Tokyo, async standard, small, a whole bunch of runtimes or async frameworks that are available to us that effectively make asynchronous programming easy. But the thing with standard is that obviously you have um, a bit of a higher level of abstraction because you actually have an operating system, and everything is sort of abstracted on top of that. The operating systems that you use, Windows, Mac, or Linux, we basically get um, we get threads. These are called operating system threads, and what async await actually does is we end up building on top of that. We build things like a multi-threaded um work stealing executor, which is something that Tokyo uses, which is quite fancy and quite interesting. Um, so async std is a little more simple. Small is, as it says, it's quite compact and it's really geared for certain environments. In the embedded async world, um, well, you'd pretty much have to do everything yourself because you still want to be able to asynchronously program, um, your application. But obviously, you don't have an operating system. We're talking about a bare metal environment. So there's a couple of things that we'll need to do. Um, you'll need to figure out, for starters, um, like we discussed in the previous async await, you know, sort of overview session, that you've got these things called futures, which are basically the result of a computation, except that the computation is an asynchronous computation. For example, um, you got a file and you basically want to pull the file into memory from disk, then that could basic if you were using threads, you'd probably have to end up blocking if it's a large file to pull, let's say, a multi-gigabyte file from the file system. Or if you were trying to do some networking, you know, something to do with networking where you're waiting to download a large piece of data, then in that case as well, you'd end up waiting if you're just plainly using a thread. So you'll end up blocking uh, for the duration of that operation till it completes. In our case, in case we don't want to do that blocking, you actually want to spend that time you were waiting for something else. You'd want to do, yeah, let's see, can we do something else during that period of time? That's basically what asynchronous programming is all about. And it's called, um, this idea is also referred to as non-blocking IO, asynchronous programming. You'll hear keywords like async await, all of them pretty much referring to the same thing. How can you know, um, improve performance by not waiting around and pretty much doing a lot more things? So that's kind of what you want to do. You can do this in the embedded context, but note that I will sort of always, get this idea about async await. You should only do it if it actually makes sense. If you really want to eke out that last bit of performance and you think you really want to uh, have a hold on the amount of resources that you're using in your system, in terms of memory usage, uh, in terms of bandwidth, etc., then this may be the best way to do this. I mean, give the reason you say this is because Async await is basically trading performance for a whole lot of complexity. Rust tries to sort of abstract out quite a few things, and that's what the future is. The future is basically an operation that will return immediately, although the actual result of that operation is still pending. All right. So you have these futures. What you need to do is you end up polling those futures and driving those futures to completion. Obviously, you don't want to end up doing things like polling, busy looping, and you keep polling that. That's not going to help because you're just going to be wasting a lot of compute cycles. And in an embedded system, you're going to be wasting a lot more. If it's a battery operated device, then you're basically continuously pushing the CPU, so you're going to burn through the battery. So that's not going to work. So you need to figure out these things called futures and how you poll them and how you move your, units of work. How you juggle between these different futures or units of work asynchronously. That's what you deal with. So basically, you have to write something called an executor, which is the thing that's actually going to do the polling. And uh, as you keep polling these futures, you either get, the abstraction is you either say that, okay, this future is ready, you're done, the operation is completed, or it's pending, you probably need to poll it again. And the way you set it up for being polled again is the entire thing that the framework does. So you'll need, another way to sort of be notified if you don't want to do busy looping that I have to poll this thing again. That means the future, once it's polled, you don't really repoll it unless it's put back on what is called the executor's queue. So I'll just sort of walk through this. So long story short, I don't want to spend too much time on that. I'd like this stream to be quite short. We are going to be looking at, so I've been looking at a bunch of embedded system async frameworks, what's out there, etc. I think there's only one technically that's really full. There's a lot of work that's being um, done on it, and there's a lot of contributors. There's a lot of interest in there. So I believe that's called Embassy. It's basically embedded async. Uh, so let's just take a look at that. So embedded async is this project right here. Yeah, it's as the name suggests, it's a framework. It's an async framework for embedded applications. And the idea is they really put in quite a bit of effort, at least from my initial glance that I've had. And that's kind of why I'm putting this little stream together. It's just as a refresher for me when I sort of come back to it. Because I wouldn't be using things like async or metaprogramming, which is macros, etc., unless it's absolutely necessary. In my case, there's a particular project that we're working on, which I can't talk about, but where you really need to think about ways to not use a lot of resources but get the best performance possible, and this is one of the ways to do that. So imagine things where you want to do things like in an embedded setting. It doesn't really make sense if you just want to do plain vanilla things like, uh, it doesn't make a lot of sense when you just want to blink an LED, etc. But obviously, that's the example I'm going to talk about. But if you want to do more complex things like you've got a bunch of tasks that are running on your system and you want to share uh, a lot of information back and forth very quickly, uh, this is probably it because async or rather asynchronous programming allows us to not use, um, primarily my point is you end up using lesser resources in terms of memory, and that's important to me. So anyway, so let's just look at this. This is quite good. Uh, it's actually batteries included, which is why I think it's quite the project. Um, there's an They actually provide hardware abstraction layers, which means the entire SoC or my MCU, or with all the peripherals, you know, on that board that we're talking about, they've already put the hardware abstraction layer together. that works with the Embassy framework. And also, one very important thing is they've got things like Embassy Time, which allows us to work with time very simply. You don't have to implement your own abstraction on top of the timer peripherals that they've got and figure out how to make those things work. They've got a way to do this, so that's good. It's low power ready. You'll see this. The executor, its job is to keep polling futures. Now, when there's no work to do, you pretty much want to put it to sleep. And you'd want to ensure that you are not using that battery. So what we can do over here is we actually have a way to put the executor to sleep, actually MCU itself to sleep when there's no work, and then wake it up when there is work to do. So that's good. And then there's a whole bunch of, as you can see very clearly, all the stuff is basically very heavy on I/O, networking, Bluetooth, LoRa, USB. All the stuff is a lot of I/O bound. That's a lot of I/O bound stuff. So it makes a lot of sense for async await. Although I'm not really sure why we have bootloaders because obviously I have a project called ROSBoot, and the core goal of a bootloader is to be as simple as possible and securely boot a system. That's about it. Any fancy stuff should be avoided in the bootloader, at least from a security standpoint. I presume it's mostly to do with downloading the firmware, although I'm not really sure you'd want it on an MCU. But anyway, so they've got an option over there, which is all good. And if you look at their documentation, so they sort of try to arrive at why we need async. They're not being, sort of cool or something like that. They say, okay, it makes sense in situations where you need it. And pretty much the idea is, if you can get away with being just doing your regular synchronous stuff, then do it. Because this does add quite a bit of complexity, as you'll see, right? So some good things, the asynchronous tasks that we have to work with, they're all statically allocated, right? That's good. And as I said, the CPU sleeps, or the executor doesn't have a lot of work to do because you can actually put it to sleep at least in the Cortex-M world. You got these instructions that will allow you to do that. And there's a lot more stuff that they're talking about. So quickly, let's just go ahead and see, how this works. So my interest is not the basics. I just want to get into exactly how it works. So let's try and take a look at that. So I've got the project opened up over here. This is the Embassy project. I hope you can see this. So in the Embassy project, we've got, so let me quickly go. I've got a board over here. Where's my board? Okay, so I've got this board. This is the NRF 52840. So simply put, all I'd like to do is, hopefully I can find this. What I'd like to do is sort of run one of their examples just to test things out. And I've actually done that. And so I just want to record all this and keep it with me for a later point in time because this may just prove to be very useful to me. Okay, so there's the examples folder over here, and they've got an example for the NRF 528. They've got a bunch of examples. If you click on source, you'll see all the examples over here. I'll just start with the most simplest one, which is blinky. Okay, so let's just look at that. Now, let me just connect my microcontroller. So if you see this, the way you write the simplest, what you call application using the Embassy framework is something like this. So it looks very simple. That's the idea. It hides a lot of stuff from you because there's a lot of abstraction going on. So the thing about async is when you really want to simply just go with it, simply just write some code, it can really look like you're working with some synchronous code. You don't have to apply your mind. But the moment you get into a little bit of complicated territory, debugging, maintenance or long-term support, etc., you really need to know how things work. All right. Basically, you need to know how async await works in Rust and the implementation, which is the specific one, how it works. So yeah, let's take a look at that. So the first thing you see is you got some imports. So there's a pretty large cargo file over here, but that's because there's a lot of examples. So let's not worry about that. Let's just look at the Blinky itself. So there's a bunch of imports. You're importing the executor, which is very important for us, and the actual hardware abstraction layer, which is called an Embassy and RF, and then there's time. This stuff is basically, you know, there's actually a different project by the Probaris folks. They also have implementations of what's called deferred formatting. So that's basically for logging. So we'll leave that as it is over there. Let's look at this. Embassy. So you basically have a main function and then you decorate that with a macro and you're done, right? Cool. Now you can just loop through a blinky that should be able to blink an LED for about 1 second over here. Now here's the thing. This particular file, I modified it if you see it. This was originally, this pin number was something else. I think it was 21. And these wait times were 300 milliseconds. I actually modified this. And that's the thing. You can quickly get something working if you just want to do the simpler stuff, the easier stuff, etc. That's also something that you can keep in mind. But since there's a macro over here, let's just go expand that, see what happens. So if we say, since I've done this, let me just expand the macro. I'll just go ahead and do that. So where is that? Macro should be here. Yep. So this is what happens. This is the complexity that's actually hidden from you. So if you see this, your imports are still here. You actually have a little more code that's now built in over here. You've got something called the Embassy main task. This is one of your tasks. This is one of your asynchronous functions. So whenever you mark something as async, this is your asynchronous function that is going to be wrapped in a future, or rather, this is basically going to return a future for you. Then there's an Embassy main, and then there's Cortex MRT main. So we'll just ignore this part. It's not that important at this point. So here's what's happening over here. When the macro expands, I just made some notes. Let's look at the notes. So when the macro expands, you create what's called an executor instance. We look at what the executor instance is. You also ensure that the executor actually is going to have a static lifetime. So that's important because it has to be around for the entire life of the application. And then you basically call the run method on the executor, passing it what's called a spawner type. The spawner is what? enqueues or onqueues. I don't know if it's enqueues or onqueues, but enqueues tasks onto what's called the executor's queue. So let's just unpack all of what I just said. So if I want to look at the executor, because this is the expanded version, I can't look at that. Let me simply just jump into, where was that? Yeah, let me go to the Blinky. And I should be able to have it. And yeah, let me go to the executor. So this is the Embassy Executor crate. So if you look at it in the lib.rs, you've got a whole bunch of stuff, not important. Since I've already seen this, let's just go jump into the executor here. So this is the implementation of the executor. Now, if you were to sort of read the documentation of this, interesting. So you can read the documentation. This is rendered, by the way, this is not on crates.io yet because it's not been published yet. But the executor that they've built is called a thread. They've got multiple different kinds of executors. You can have one in the interrupt mode, which I don't think I'll be talking about right now. We'll just talk about the thread mode one, which is the lowest privileged one. All right. It basically does the job. It has, so in any implementation of async await, you will probably have an executor and it will probably consist of some sort of a queue. The queue into which you insert you add your futures. And generally, when you talk about a future, the future is always going to be wrapped in what's called a task abstraction, right? So the future is actually the task, but you also need more information about the future. So you sort of have a task and you manage more of that information in there. And that's kind of what if you look over here, futures are stored in this type called the task storage type in Embassy. And the task storage type actually contains a task header along with the actual future. Okay, we will look at that. So let's go look at that first. But before I do that, I'm just going to be jumping back and forth between the expanded macro because we're only looking at the blinky code. We just want to make sense of how everything is built out. The documentation tells you stuff. It's a good place to start, but nothing's better than the implementation itself. So if you see here, we instantiate our executor. We make it static. The reason we make it static is because there's actually a reason here. So let me get to that reason. So yeah, as you can see, when we this function requires static mute self. This means that you have to store the executor instance in a place where it will live forever and grants mutable access. So they want the executor to actually, by design, it needs to live forever. That's it. That's why we have this additional piece, which is make static, which is, of course, all of this stuff is unsafe. You're doing a transmutation over here. So great. Anyway, that's good. Now the executor, you're trying to go ahead and run the, just call the run method on the executor. Let's see what that does, because we've already seen it here. This thing runs the executor. What it takes is the closure, and the closure accepts what the spawner type that I briefly alluded to. The job of the spawner type is to keep, adding these futures or tasks to the executor, specifically the queue of the executor. The init task is a little different. It basically, after it runs, all the other tasks get run. So it's a little special in that case. So there's an initial task as well. And you keep the spawner type around for however long you want because you can keep spawning more tasks. That means whenever you want to push a task onto the executor, you need this thing. That's how you'd, work with the executor over here. And, well, this function never returns. So that's the whole point. So this is always running. Because it's always running, you want to ensure that it goes to sleep when it has no work. That's the whole point of the, wait for event and signal event instructions that we use on Cortex-M. So that's how you sort of put things to sleep and bring them back up. Okay, so here's the run method. Let me pull the run method out. Where is that? Yeah, so let's go look at the run method. Run method's pretty simple. It takes the closure, which is init closure. And basically, if you look at the executor here, what is the executor? The executor has got, it's basically, multiple levels of indirection. The inner is the actual executor. If you were to look at it, this is where your run queue is. This is the actual queue. But note, the actual queue that you have is what's called an atomic task queue. So effectively, you're just holding on to the head of what is called a linked list. And this is lock-free because you're using atomics. All right. So you just keep, extending the head of the list, and all the other items that are there are basically nodes that contain futures in this linked list kind of a task queue. So yeah, there's not much here. This is pretty straightforward in terms of that. We'll get to the part of how you queue up stuff and you dequeue stuff and all of that stuff. So that's the executor. So just a little bit of abstraction over there. Now, what we were looking at was, we wanted to figure out how the spawner actually does what it does. So we pull in the inner, and then we call spawner on it. spawner basically returns us the type that we want, which is a spawner type, which is what will allow us to spawn tasks onto an executor, right? So that's cool. So we know that much now. So that's good. So we know that we've got an executor, it's got a queue, we can spawn tasks into it, and that's kind of what we have here on our blinky, right? So spawner must spawn is the other piece. So if you go look at that, yeah, so let me just do that. So the spawner will actually, when you do smart spawn, it's nothing but calling spawn. So it's just little bit of an indirection. What's interesting about this crate is there's, as I said, there's quite a lot of thought that went into it. There are tiny bits of optimizations everywhere. In fact, this is one of them. If you read this, must spawn the task onto an executor, panicking on failure, which is great, but this is actually used by the main macro that we're using to throw an error when the spawn fails without introducing a deformat feature in the Embassy macros package, which would require something called name -z namespace features. So this stuff, this is what I like about this particular crate. It really does address a lot of stuff that you would want to think about when building your own applications or async applications. There's a lot of the stuff that I keep seeing around. But anyway, so spawner spawns the task. What does it actually spawn? Let's go look at that. So it's basically spawning the initial task. And here's where we'll come into our task storage pieces. So let's look at the Embassy main. What's being spawned is this type alias called fut, which is basically saying that anything that implements the future is what I'm looking at and also has a static lifetime. Pool size is just a use size, and pool is this thing called the task pool type. Now, we haven't talked about that, but we've sort of touched what is task storage. So let's go look at that. So I've sort of done this, so I know my way around this particular crate. So, but yeah, it's pretty straightforward if you just get to know it. Okay, so let's start at task. So this is your task storage. As I said, every future that you end up representing in code, you'd want a way to represent that. And the way they do it, the way they actually represent futures is they actually, put it in something called the task storage. As I said, it's the raw storage in which a task can be spawned. The future is this uninitialized cell, but that's again nothing more than a maybe uninitialized. It's a wrapper around maybe uninitialized. Well, you can actually see that. That's what it is, which is good. I haven't figured out why you'd want this, but anyway, it's probably required for something. And then you've also got the header. The header is very interesting. It's got quite a few things. This is the raw task header. So the state of the future, there's about 3 states. Either the task is spawned, that means you've created it, then you put it in the run queue, or it's in the timer queue. The timer queue is a little separate. So you basically have these 3 states, and that's an atomic. And the task header is going to say, okay, there's also something called the run queue item. Basically, the item in the run queue. I'll get to that. You also have a reference to the executor itself. And here's the thing. This is a little bit of a flipped way of doing things. You are also storing a pointer to the polling function. The future that gets polled, how does it get polled actually? You're actually storing a reference to that. We'll see that there's a little bit of a indirection over there. But yeah, this is your task header. So this is some metadata about your particular task that you'd like to store along with your actual future. Okay, so that's what we see here. In the futures are stored in task storage, which consists of a task header and contains some metadata about the task and the actual future itself. Now let's get to the job of the executor. Its job is to dequeue the futures from its run queue, which in this case is an atomic linked list. and then this call poll in there, right? So let's look at that. Uh, so what happens when the executor actually calls poll, right? So let's just go look at that. But before we do that, let's just keep following the expanded blinky RS. You see, okay, we were talking about the task pool, so let me just cover that as well, just in case, we miss out. There's not much in the task pool. It's just, the task pool is basically an array of task storages. That's it. That's literally it. Uh, where is that? Yeah, yeah. So literally a task storage array. That's it. So you can actually create one of these uh, right here. So you're basically saying, I'm going to create an array of task storages, which basically an array of futures, and I'm going to call this spawn async function. The goal of this is basically doing all the setup to load the main async task. This is your main async task that you actually want to load. All right. This is where most of the work the actual work happens, not most of the work. So if you see this, the first thing that happens is we use the Embassy NRF crate to initialize our entire, uh, basically our entire hardware abstraction, or you can say to initialize all the peripherals. Okay, that's what this init method actually does. This includes all the peripherals, timers, etc. that you need. They're all being initialized. None of this is async. All this stuff is, you don't wait for it. You just, it completes. It's not, you don't need async to wait for that. You also set up an LED because you want to do the blinking. Oh, but by the way, I forgot to actually show you if this works or not. So let me actually flash this correctly. And so you can see this, it's flashing. Yeah, it's done. So that's blinking. Red LED is blinking. Great. So let me just stop that. Okay. Yeah, so that's cool. It's blinking. Mission accomplished. So anyway, so it's definitely blinking, and this is what we just wrote. Everything else is just, the macro expansion or boilerplate that's already automatically doing the setup for you. So you see that, we're doing the initialization over here, and then we're creating a new LED pin. It's all great. Then we simply go ahead and keep looping through. There's no, we're not setting up an interrupt or something like that to wait for an LED, etc. We're doing none of that. This is basically saying you're looping through, setting the LED high, then waiting for a little bit, setting the LED low. It might look like, um, this is it. This shouldn't be working, right? Now, that's the part about this. The thing that's actually what you're interested in is the place where you're calling a wait. This thing called the timer is actually our future. It implements the future trait, right? So it's doing that. So it implements the future trait, which means we are basically representing the timer, this particular type, to be something that completes at a specified instance, as it says. All right, so let's just follow through this and see how that works. But before that, let's just go through the notes over here. So we want the executor to basically treat the timer future as a future, and then whenever it hits the wait point, it calls poll on it and say that a wait point calls poll on it. But that it pulls the future out of the run queue because it's already there, pulls it out of there, and then basically polls it. When you poll it, you end up trying to drive that timer to completion, and then you're done, right? So let's just look at that part. The poll call. So here's how that works. The executor, which in our case is here, it's going to go ahead and call something called the poll method on it, which is on the inner, the actual executor is going to call poll on it. If you go look at it, you will see, okay, there's a little more indirection here, but you will see that we'll get to this part, the dequeuing, expired stuff, etc. So first things first, it goes ahead and dequeues the, the futures in the queue, and you end up calling, you end up getting the header part of each of the futures or each of these tasks that you're interested in. And then you check the state, all that's great. And then finally you go ahead and actually run the task. This is the actual part where you do the poll. Right? Remember we looked at in the task storage, in the task header section, you actually have the poll function itself, a pointer to the thing that's actually going to be doing the polling. That's what we're interested in. So if you think about it, timer's poll function, timer's poll function comes from its implementation of the future trait. And if you come here and look at its poll function, you see that, great, if it's ready, that means if it's completed, if it's basically yielded or it's completed, you yield ready. Otherwise, you basically schedule for a wake up. And you pass in what's called a waker and all right? So this is all the regular stuff. I mean, you could probably see the previous, or even I could see the previous async await stream if I forget or something. But yeah, this is all the regular stuff. This is all built. For example, the future trait, everything else is already part of the core library itself. So if you go look at it, yeah, it is part of the core library. Anyway, so the executor is going to pick these futures from its queue, call poll on it, which inevitably ends up polling the future, and you end up doing this. So you either get a ready, if it's ready, or you get a pending. But before you get that pending, you're going to schedule for a wake up. Now, what does this actually mean? It means that, technically, when you do something like this, it means that notify me when this is ready. In other words, put this future back on the queue when it's ready so that I will go ahead and poll it again. And then when I poll it the second time, I know that this is ready, so it's going to complete. Right? So basically that's it. And the way you do that is you've got this thing called the waker type, which you pass on to whoever, is going to notify you. In the context of embedded systems, usually when we're dealing with things like peripherals, etc., we're talking about interrupts, because it fits nicely with the asynchronous model. So you're doing some work, you set a timer, maybe you're doing some work not just a timer, but you're doing some work. Let's assume there's a button that you press. That button is going to sort of throw an interrupt, right? So if there's some execution happening and you hit the button, it's going to raise an interrupt, which will basically invoke an interrupt handler, which changes the peripheral state. At the same time, you could also go ahead and notify the executor, to say that, okay, this thing's already changed, so please, poll this thing. You'll probably get an answer right now. So yeah, that's kind of what schedule wake, or rather this whole asynchronous part is about. So the executor's job is to just keep polling and keep driving that future forward. But there's this other thing, other mechanism in embedded systems that usually interrupt handlers, and other things. In Tokyo, etc., there's a little more. You've got things like reactors, etc., that do all of this stuff for you. At the end of the day, you end up doing something, like calling epoll, etc. But effectively, let's just talk about the embedded world. We're just using interrupts over here, technically, right? Because that's kind of what we have to be notified when something's ready, if you want to avoid busy looping. Okay, great. So now we know that we know that the job of the executor is to dequeue stuff and then call poll. Here's the other thing: when you actually see this, when we call poll, right after we call poll, we're going to call wait for event. So we're putting the executor to sleep. Now, technically, when that happens, that's great. But then you end up on queuing a task, the new task onto the futures, so the executor's queue. That the act of on queuing a task will also trigger the wake up call, which is SEV in this case. You could actually see that. What is that? Yeah, you could. Let me pull it up here. Mm, yeah. So we're looking at poll. Yeah, okay, got it. We're looking at poll. We saw this, and yeah. So if you see this, this is the other part I was talking about. There's also a timer queue, uh, which pretty much is part of the executor itself. And it's going to do this thing called check if uh, any of the tasks have already expired. So we're going to be actually attaching an expiry time to each of these tasks. If they've expired, just dequeue them, all right? And the way that actually works is you end up calling um, what's called wake task. Um, Wake task is basically, the waker actually calling this. Um, yeah, the waker is actually be notifying, saying that okay, there's some progress to be made. Please put this thing back on the queue, right? So if you go look at this, if you go look at this, you will see that that's exactly what we do. All of this stuff is just setting up stuff, but we end up you know on queuing back onto the executor. So once you on queue something back onto the executor, you're good. You have gone ahead and put the task back onto the queue so that it'll be pulled again. Uh, so that's good. So we know that whenever you on queue something, this is what's going to happen. But at the same time, what's interesting is this on queue. What does it actually do? The on queue is whenever you call on queue, you will end up actually signaling the SEV instruction. All right. And the place where we can see this is you actually end up calling Pender. There's there's a way that this actually works. Let me find that out for you. So yeah, there's quite a few tasks over here. So this does it does take a while to sort of navigate all the types and follow all the types over here. But in any case, let me see if I can find that for you. Uh, where is that? Yeah. So there's this pender function. If you see this over here, uh, it's simple. The pender is going to say, bring it out whenever the task is woken up, bring it out of the out of sleep. SEV is what we're doing over here. So bring it out of that. And the other way of looking at this is if you, where did I go? Yeah. Yeah. So you see, if you actually call on queue over here, which is uh, the method that you're using over here, if you actually call on queue, you will end up calling pend. And when you call pend, well, it actually, you do the self run queue on queue, and then you do self dot pender. So if you call that, if that works out, we will be able to call pend. And pend actually calls pender, which we just saw is the this particular instruction. So you'll end up waking uh, the executor that's already gone to sleep. This is particularly for the thread mode executor. For the interrupt context one, it's a little different. You use interrupts over there, is what I understand. But great. So all that's good. Um, so we've got that done. Now, whenever we do this, at least in our case, we were doing the timer, we were looking at the timer application. So we do LED set, this is synchronous. When we do timer, we already saw that, you call the poll method, you poll, you're either ready or you go ahead and schedule for wake up. When you schedule for wake up, you end up actually just setting the expiration time. You store that. So let me just show you that. So I'm a little unsure because I do think that there is some sort of continuous polling going on, but I may be wrong. At least from the implementation, that's kind of what I get. So when you do the polling on the timer, this is what happens. So let's just say that it's not ready. The timer is not expired yet. So if I go here, the other thing is all these calls are basically external Rust functions. They didn't want to use traits, etc., because I believe that saves them uh, some, some space, I guess. I'm guessing. But yeah, we'll know. But if you go look at where this is, you will see that this is your timer queue, and all of this stuff is just a macro implementation. But when we end up calling schedule wake, this schedule wake is something that we should be able to see here. Yeah, because it's a macro, I can't just jump into it. I'll have to search for it. Right. Yeah, this is the one I was talking about. So this is an implementation. You end up storing the the expiration time, basically that you want, which is the at expiration time. You end up storing that directly in your task itself. All right. And what happens is you keep checking to see if it's DQ'd, if it's not DQ'd, if the timer is expired. If it's not expired, you end up pushing back, you end up on queuing the future back onto the queue, sorry, the executor's queue, and you keep polling that. I presume that's how you're supposed to do this, right? Yeah. I don't think we're using interrupts. So, okay. Yeah, I think I answered my question. But anyway, I hope that sort of made sense. So when we poll the time of future, we basically end up here if we are pending, and the we store the expiration time in the task itself. And then, as you've seen in the run queue, uh, sorry, where did I go? Yeah, as you've seen in the executor's crate, if you go look at, yeah, this is it, no? Yeah, as you see over here, when we do the DQ expired, if there's no expiration, we're going to put the task back on the queue. At least the expiration, uh, the expiration timer. We're going to put it back. So when we do that, we'll end up polling it again, right? So that's sort of how we keep running through this. Uh, so I don't really think that in every case you end up doing busy looping, but I guess at least in the timer's case, you would want to go ahead and do this looping because it's a timer. In any case, so that's how this works. We've already seen the fact, I think, I've covered all these points. We've already seen that, how the executor does not do work when it has no work to do. We've already seen that happen. The only last piece that I would actually talk about is this is all great. All of this looks very interesting, but where is the actual time driver, right? In order to see that, let's go look at, so this is Embassy time. This is where, you've got your, it provides a driver for you. So the driver over here is basically just a crate. It says, okay, you implement the driver trait, you implement all these methods, you're pretty much implementing a driver. The actual implementation of it is in Embassy NRF. And if you see this over here, you should be able to see a time driver. All right. The time driver over here is RTC. It's quite straightforward. The first thing is you get the register block. All right. And then this is what's calculating the now time frame. The alarm state is not important, but the abstraction over that is RTC. So this is think of this as your driver, all right? You initialize this. As I said, the initialization already happens in the init phase. So that's already done. You don't have to do it for yourself right now. And then the interesting thing over here is we get the time from here. The way we get the time is if we look at the abstraction that's being provided over here, we see that there's a now, right? That now is actually what's called, if you noticed in our poll function, whenever you're polling the timer. So for example, whenever you're polling the timer, here, we're actually going to be looking at the instance that you're sort of polling. So because we were looking at, let me show you this. We were saying after 1,000 milliseconds or 1 second. If you go in here and then you actually look at it, what we're trying to see is we're basically trying to compute what's called a duration. You compute that duration from an instance as well. So you get the duration and you add it to the duration. Now you have the timer. So the current instant plus the duration of 1,000 milliseconds, you have the timer that you want. And then you keep waiting for that timer, checking to see if that timer is expired. I guess that's how it works. So yeah, so the way you implement timers is you do end up polling again and again till the timer expires. Although I would have thought that there is a peripheral that actually where you can just set the timer and wait for it, get an interrupt when it expires. Yeah, that part is something that I'm a little confused. But in any case, so that's good. So pretty much that's kind of what we're doing over here. Instance now is when you actually do this, you end up here and you call the driver now, which effectively calls the actual driver. And they're already telling you how to implement it. So yeah, that's like a whirlwind tour of the Embassy framework with the most simplest example. But the key idea over here is you're doing things like direct memory access, which means without using the processor, you want to directly access peripherals and probably do some DMA transfers. Or you have a lot of tasks or some tasks and you need a really fast way to communicate amongst those tasks and share data. Or you have some sort of I/O, like all the different protocols that you saw, which is Bluetooth, networking stuff, TCP, all of that stuff. I think this makes a lot of sense to use. But as you can see, async is not without its complexity. There is quite a bit of complexity. Now imagine debugging a problem, not for Blinky, but for something that's a little more interesting. Well, you can see how it can get complicated. So you are trading performance for complexity by its very nature. And this has nothing to do with Embassy. This is basically async itself. So, but here's a good thing. You can also have a whole number of examples for buffered, UART, You got channels, you got Ethernet, GPIoT. There's a whole bunch of examples for just this board alone. So there's a lot of stuff that you can do. What I'm very interested in is the MVMC, which is what you can use to pull data from the uh, the memory controller, which is basically the flash module. Uh, so that's good. So there's a lot of stuff over here. So, but basically, just to recap, uh, when we talk about Embassy Async, there's a lot of abstraction that's hidden from you, the user, but it does a pretty good job, though, I must say. So you start off with the main macro. The main macro is essentially what sets up things for you, creates an executor, ensures that you know that the async tasks that you have set up is actually going to be called. You have this thing called the spawner that will allow you to keep spawning tasks into the executor. And tasks are usually represented with this task storage type. It's got a header and the actual future in it. So the job of the executor is once it starts running, its job is to just keep dequeuing stuff from its queue, keep calling poll on each one of the futures that it has. And whenever you enqueue, queue on queue any other task, uh, usually when you call poll on the task, it's going to call poll and then go to sleep. When you enqueue something, it's going to wake it up, right back up using this wait for event and signal event instructions that are part of the ARM Cortex-M instruction set. And then anything that you want to actually, sort of turn into uh, this future thing, you basically implement the future for it. For example, here the timer future is implemented, and you end up polling it, and then you keep moving forward. There's a lot of metadata attached to each future in the task header. We attach the poll function itself, we attach the timer, we have the state maintained, obviously we need that. So all of that stuff is maintained here. So great. And then the interesting thing is this part, which is where we say we see none of this is possible without the actual hardware. So the timer peripheral is abstracted out for you. You got the HAL for you. It's already built into Embassy. If you have a board that is not supported, then you probably have to write all of the stuff for you and sort of make it work. I don't think that's difficult. I haven't looked at it, but should be fairly straightforward because they are reusing a lot of the existing HALs, is my understanding. And there's this abstraction of a timer queue where you can basically just keep adding the timers that you're interested in, that is, and then keep sort of working through them. All of this is abstracted out in Embassy time. And for the wake up part, apart from the existing stuff that we talked about, whenever a future is polled, we pass in the waker type, then the waker is used. The waker thing is the thing that you can actually call wake on, which is going to do the notification to the executor to say, okay, this thing that you asked for, it's ready now, you can poll it now. So let me put the future that you've previously polled back onto your queue. All right, so that's about it. And that's Embassy. There's interesting documentation. There's quite a few, there's a bunch of things that I haven't talked about, but I think this sort of pretty much sums it up. I didn't talk about the interrupt executor, but it's, if you want to get into it, we can, that's something that you can look at. But anyway, it's quite interesting. The thing that I also like is this particular statement, which is there's no fixed capacity data structures because we're using that linked list, atomic linked list queue. So that's good. So there's a lot of good things going for it, but yeah, a lot of abstraction, and the complexity is hidden in that abstraction. Yeah, that's the biggest thing that I think is the problem. And I don't think this is to do with Embassy Async, as I said, it's just async await. That's just it. The other thing that I would certainly be interested in is to see how you would debug all of this stuff. and how you would visualize, let's say, performance bottlenecks, etc. That would be interesting. I'm pretty sure there's probably ways to do that that I'm not aware of. Okay, anyway, I think that's long enough now. So just another random stream. So if anyone watches this, thank you for watching this. And if you have any questions, just let me know and I'll see how I can answer them. Thank you.